you all for attending. We get many technical support questions that come in RISA regarding hot-rolled steel, and so we figured we would put on a webinar to address some of the most common questions that come in so that you can better understand how to use hot-rolled steel design within RISA 3D and RISA Floor. Today we're going to be taking a look at RISA 3D version 9.1 and RISA Floor version 5.1. These new versions were recently released, and many of you who are under maintenance with us have probably already received them in the mail already. These new versions do incorporate some new features relating to a variety of things in steel, one of which is the single angle bending checks, which we'll be talking about today. So just as a heads up, if some of the things that you see in the program today don't exist on your version that you're running, you might check and see maybe you're not running the current version, which is 9.1 of 3D and 5.1 of Floor. Now today we're going to be talking about three different documents, and we're going to be referring to these when we talk about the design of hot-rolled steel within RISA. The first and foremost is the AISC 36005. That's the 13th edition steel construction manual. The second is Design Guide number 9, and that's a steel design guide specifically relating to torsion within members, and we're going to be talking about torsion today. And another one is Design Guide 11, and that relates to floor vibrations due to human activity. And we're going to see how to take a look at each one of these aspects of steel design within RISA. So here are the topics we're going to take a look at. The direct analysis method, and that relates to things like P-Delta, stiffness adjustments, and notional loads. We're going to take a look at warping torsion within the program. Single angles, and that is how do single angles behave differently from other members. We're going to take a look at floor vibrations, and then lastly, steel joists. So to start with, let's talk about the direct analysis method for a moment. And this relates to designing buildings that are going to have sufficient stability. And stability is referred to under Chapter C of the AISC specification. And what you'll see in the 13th edition is that they list some traditional means of accounting for stability, and this includes some things like the old-fashioned B1 and B2 factor methods. But then they also refer to Appendix 7 in the specification. Now, in the upcoming 14th edition, the contents of Appendix 7 have actually now been placed in Chapter C, and they now are the official way to do stability design. But in the 13th edition, they are still technically an option, although you'll find that they are the best way to go in terms of accounting for stability within a structure. So we're going to take a look at Appendix 7, and that is the direct analysis method. Now, the direct analysis method requires three things of your structure in order to guarantee its stability. Number one is that you need to do a full second-order analysis. And that second-order analysis means accounting for P large delta effects and P small delta effects. And we'll get into in a moment what that exactly means. The second is that you need to account for a stiffness reduction in your members, and that is the EI star and EA star respectively. And the third is that you need to apply notional loads to your structure. So to start with, when we're going to take a look at P-Delta, let's take a look at this cantilever column problem. So as you can see in the image here, if I have a W12 by 45 column, I'm going to be applying 200 kips of gravity load to it and a 10 kip lateral load right at the top. And you'll see this is a cantilevered column as it's fixed down at the base and free up at the top, and it's a 12-foot tall member. So what we're going to do is I'm going to open up a RISA 3D model containing this column. And we want to take a look at the P-Delta effects that come about as a result of this column. Now, what exactly does P-Delta mean? Well, I can tell you right now the P is that 200 kip load that's on top of the column, and the delta is the deflection that we're going to get in that column. So to start with, you'll see I have this model created, and if I come into my load combination spreadsheet, you'll see that I have P-Delta turned off right now. What I'm going to do is I'm going to solve this load combination, and I'm going to just get a warning there that I didn't run my P-Delta analysis, which is required per the 13th edition. And what we can see here is I'm going to come up and turn on the deflected shape. And so there's the deflected shape in my column. It's being pushed over this way. Now when we solve this, if I take a look at a detail report for this column, we're going to see that 200 kip axial load, and we're going to see a 120 kip foot moment that's on this column. And that's simply equal to the 10 kip load laterally multiplied by a 12-foot tall column. But what we're missing out on here is what's known as secondary effects. And the secondary effect in this case relates to the fact that this 200 kip load moved with the top of the column. It's not as though it remained here while the column deflected. Instead, this 200 kip load is now pulled over to this location right here. However, the base of the column remains exactly where it was. As a result, we now have an offset equal to P, the axial load, multiplied by delta, the deflection of this column, and P times delta creates a moment, and that's going to be an additional moment that's in this column. Well, how do we determine that? It ends up becoming a multi-step process. You see, inherently, when we solve without P delta on, what we're taking a look at is what's known as a linear analysis. That is, the farther that I put, or the more load that I push on this column, the farther over it's going to bend in this direction. But we're not accounting for additional factors, those being those secondary moments, that are going to add up into the column and that are going to lead it to want to collapse. So what we can do is we can actually manually take a look at what the P delta effects are going to be on this column. In order to do that, I'm going to create a copy of this column. So I'm going to come up here and create a copy. In the Z direction, I'm going to copy that back 3 feet, 36 inches. We've created this copy here. And now when I solve my model, what I can do is take a look at the joint deflection for N2. And so we'll come up here and take a look at that, and we'll see the joint deflection for N2 is 0.981 inches. What I can do is come over to this new copy I've created, and I'm going to redefine the top of it so that its x-coordinate is that 0.981 inches. So what we've done is we've leaned this column, and we're effectively creating now a model of the already deflected shape. And from this already deflected shape, we now are going to capture that P delta, that is the fact that this 200 kips is no longer aligned now with the base of the column. And when I solve this, and I take a look at the joint deflections now, we're going to see that this new column that I've created ends up leaning over a little farther, because the new moment that I've placed on there is going to actually place a little bit more energy in the column that's going to cause it to lean a little bit farther. So when I come to my joint deflection spreadsheet now, we can see our new deflection is 1.114 inches. Well, let's do the same thing here. I'm going to copy this column back another 36 inches, and I'm going to set its top node now to be 1.114 inches. So now when I go back and solve again, we'll see now we're at 1.132. I'll go ahead and create another copy. We'll bring that one back, and we'll set it to 1.132. And now solving this one, and taking a look at the joint deflection at N8, you can see we're at 1.134. So right within this model, what we can see here is an iterative progression from N2, 4, 6, and 8. And what you can see here is that we're clearly converging upon a solution. That is, there is a final deflected shape that the column was eventually going to settle into, and it's probably going to be somewhere on the order of 1.135 inches from what we can see. Now, this is an actual physical phenomenon, and it's necessary to do an iterative solving process in order to capture this sort of phenomenon in a linear elastic solver like we have in RISA 3D. Now, what we can do is, rather than setting up a complex model like this, instead, we can just turn on P delta analysis within the program. So if I come over here to my data entry toolbar, under the load combination spreadsheet, in this P delta column, I'm going to put a Y in here for yes, solve for P delta. And what we're going to find now is that when I solve this model and we take a look at the original column, that we see its deflection is reported as 1.135 inches, which is exactly what we were approaching as we created this. So the program behind the scenes basically was able to do iterative deflections of this column in order to find out what the final result was going to be. Now, we do this by a method called virtual shears, and it's basically a shortcut method in finite element analysis that allows us to place imaginary additional shears on this column in order to reach the final deflected shape. And that is different from a true nonlinear solver, which we don't have. As a nonlinear solver, would cause the program to slow down considerably, as it would have to rebuild stiffness matrices for each one of these columns each time we created a copy. So now you can see how P-Delta works in that regard. Okay, so we had our initial shear of 10 kips on that column, initial moment of 120 foot kips, and initial deflection of 0.981 inches on here. Now, the initial deflection, when you calculate that from that 10 kips, is just based off of PL cubed over 3EI, but that is a bit of an oversimplification. You see, there's two things you need to account for in beam deflection in real life, and that is the bending deflection and the shear deflection that's associated with it. Now, back in school, when we were all taking statics and mechanics of materials, we tended to ignore the shear deflection on beam elements, because if a beam is long enough, the shear deflection becomes a relatively inconsequential component. But of course, as your length to depth ratio decreases, shear deflection plays a larger and larger part. And you can see here even that theoretically, when we calculate this, that the bending deflection on that column is 0.981 inches, and the theoretical shear deflection that would be additive to the bending deflection is an additional 0.035 inches. Now, if I go back into RISA 3D here, and I'm going to come up to my global parameters, you'll see that under global parameters, under the solution tab, there's this checkbox for shear deformation. By default, this is usually turned on, but I turned it off for this model, and you can always take a look at this within any of your models to see whether or not that shear deformation or that shear deflection is being considered. And so now you'll see that when I turn that on, and I'm going to go back and shut off my P-Delta results for a moment, we are going to have now a joint deflection reported. Instead of 0.981 inches, it's going to be 1.016 inches of initial deflection on here, and that's simply the sum of the bending deflection and the shear deflection. So we are able to account for that. Now, of course, the additional shear deflection is also going to get added up in the P-Delta effect, such that when I run it with P-Delta and shear deflection on, now we get a final deflected shape of 1.182 inches. Now, the actual deflection that we're getting in here probably isn't going to be important to us in terms of model design. What is going to be important to us is going to be the bending moment and shear and other forces that are existing in this column. So when I take a look at a detail report for the column, you'll now see, rather than 120 kip feet of moment, we now have 140 kip feet of moment. So certainly, an increase in moment in the column that without running that P-Delta analysis, we never would have been aware of. Now, oftentimes when you're solving a model, you may run into a situation where when you solve, you get a P-Delta divergence. That is, the program actually halts your solution and it says P-Delta was diverging, could not come up with the solution. Well, when we took a look at the progression of deflections on these nodes, I pointed out that we were converging upon a final solution. However, if our column is terribly flimsy, then we're actually going to diverge from that solution. So let's come in and take a look at that for a moment. I'm going to shut off P-Delta, and we're going to take this column, which is a W12 by 45, and let's change its shape instead to be, say, a W8 by 15, something very flimsy. And so now when we subject that W8 by 15 to the same loads, when I solve this, we're going to get an initial deflection at N2 here of 7.22 inches. Now, if I come in and I set up, say, all of these columns here to be that W8 by 15 through my section sets, and I take that initial, let's go back and solve that one more time to get the number again, 7.221 inches of deflection on this column, note how far that leans, and when I solve it and place that 200 kip load on there again, now we get 14 inches of deflection. And so if I come back in here and set N6 to be 14, what you're going to see is that we're going to have a steadily diverging result. Now we're up to 21 inches. So each iteration that we solve, this column leans over another 7 inches. And you can see where this is heading. Rather than converging upon a final solution, this column is going to outright fall over. That's what's happening in the program when you get a P-Delta divergence error. Is the program's telling you that in reality, when we run the iterative process, your structure is actually collapsing due to lack of stiffness. The most common thing that happens that results in this is that you've sized all of your columns for gravity-only loads, and then you start applying lateral loads to the structure. And when you apply a lateral load to a relatively flimsy gravity-only column, things will tend to just tip over. So usually when you see that, the first thing to take a look at is to shut off your P-Delta and take a look at your deflected shapes, because those deflected shapes can tell you a lot about how the structure is behaving. And wow, look at that. We can see right here with that W8 by 15, these things are just flopping right over. So that would tell you right away, hey, maybe I need to bump this up to a beefier column section, like a W12 by 45, and now we don't get nearly as much deflection, and we can actually get a convergence on P-Delta as opposed to a divergence. That's one very important thing to consider. So, when we took a look at the P large delta, and P large delta is what we were just taking a look at, you'll notice this capital delta. That is the consideration of the deflection between the top of the column and the bottom of the column, or in other words, the deformation from floor to floor in a structure typically. We note that we get an 11.6 kip final shear, about 139, 140 kip feet a moment, and that final deflection. That's a 16% increase over our standard elastic analysis, which we started off with. And this is the sort of analysis that we would have done back in the old 9th edition days, before we had to consider things like P-Delta. All right, so now the next thing we need to take a look at is we need to take a look at the effects of what's called P-little delta. So for that, I'm going to pull up another model here, which is that same column that we've been taking a look at. And what we've done in here is we've gotten a bit more refined with this model. So here I've actually broken the column up into multiple segments, and when I solve this now, what we're going to see is a more accurate deflection that actually captures the curvature of the column as we go up. So the way I created this model was I first initially created this column with 3 intermediate nodes along it, and then I took a look at the deflection of each one of those nodes, and I applied that here where I actually have the column broken up into multiple pieces. And so you can see, even in the undeflected shape, that we have this sort of curvature coming out here representing the shape of the column. This is what's known as the P little delta effect, that is P small delta. And the P small delta effect accounts for the fact that the axial load is not only moving along with the top of the column, but the axial load carries through the column. So any sort of curvature that we get in our compression members, such as our columns, is also going to have a contribution to the overall design. Now, if I come in here and turn on P-Delta for this model, and we go ahead and solve it, I can take a look at the member forces for this column, and we'll see that now we're up at 140.2 kip feet. And in the previous model, where we were solving P large delta by itself, we were at about 139.8. So you can see there's a very negligible amount of contribution that we're getting from this P small delta effect. Next to nothing. In this case, it's 0.4 kip feet. So that tells us right there that for this particular example, P small delta was not as large of a concern. Now, what's the difference between P large delta and P small delta as far as we're concerned for analysis? Well, the difference is whether or not I've placed these intermediate nodes along a column. Now, I'll show you in the program how you would place these nodes in. I'm going to delete the ones that I had already put in place. When you're in the program, if you come up to Modify up at the top, we have an option called Split Members. And in Split Members, what I can do is split any member into a number of equal pieces, either by actually splitting it into that number of different pieces, or by just adding joints along its length as a physical member. And I'm going to go with this second option and click on this member so that now I've added these joints. So my difference in results between adding those joints or not is going to be noticeable when I run my P-Delta analysis. And as for the amount of difference, well, it depends on your structure. Now, the 13th edition makes a big point to say, hey, you need to consider both P large and P small delta in all of your analyses. And this is true. In order to get the maximum level of accuracy, you certainly have to. But what you'll probably find in practice is that most realistic building structures, and even other types of structures as well, the columns are stout enough that they don't have a significant amount of curvature or bowing that's occurring in them, even in the case of things like cantilevered columns and moment frames. So as a result, the P small delta effect can be considered nearly negligible. So what I would recommend in a typical model is that perhaps you solve the model without having placed these intermediate nodes along your columns, and then do a save as with your model and try using that split member tool to add the intermediate nodes along your column. Solve the model and see how much different your results are. Typically, they're going to change by less than 1%, which tells you that the P small delta contribution to the overall P delta effect is negligible. And so therefore, you can go with your original model and you don't have to complicate it or clutter it up by adding these additional nodes along the length. So there, from the P small delta analysis, we ended up with a slightly larger final moment on here and a slightly larger deflection as well, but still something important to consider. And of course, RISA is not placing those intermediate nodes for you along the length, so in order to get your true P-delta analysis, you need to both go to the P-delta spreadsheet, the load combination spreadsheet and say Y under P-delta, and you need to add a number of intermediate nodes along the length of your member. Now, because things like columns don't typically have a very complex form of curvature, and you're typically only going to see 1 or 2 points of inflection along the length of a column, you can usually capture the effects appropriately just by placing 3 nodes intermediately along there. That is, 1 at the midpoint and then 1 at the quarter points as well. So now what we've done in this model is we've met all of the second-order analysis requirements for it. The next thing that we need to do is take a look at stiffness adjustment. This is also required per the 13th edition. And in the stiffness adjustment, what they tell us is that in order to account for certain effects within the structure, we need to, in our analysis, reduce the stiffness of all of our lateral members. Now, a lateral member is a member that is considered to be participating as part of our lateral resisting system. And the stiffness adjustment we need to do axially on members is rather simple. Basically, EA star, EA is your stiffness, that's the modulus of elasticity times the area, and this is the modified stiffness, is just equal to 0.8 times EA. So we just take a 20% across-the-board reduction in stiffness axially of all of our columns and such. Now, flexurally, it gets a little bit more complicated. You see, for the flexural stiffness reduction, we're going to take 0.8 times this value tau sub b. And tau sub b is a function of the axial force in a member divided by its axial capacity. Well, here we run into an issue relating to finite element solving of a model. That is, that when we have a statically indeterminate system and we solve it using a finite element analysis method, we determine the force in the member based on the stiffness of the member. That's an inherent thing that goes all the way back to even the virtual work stiffness methods that you would do for any sort of indeterminate structure. Well, now when we take a look at this, the AISC is directly telling us that the stiffness of the member is dependent on the force that's in that member. So if the force is dependent on the stiffness and the stiffness is dependent on the force, we end up in sort of a loop here. And the only way to get around that is to do another iterative process. And so what we can do is we can actually start off by assuming that tau sub b, say, is equal to some start value of 1.0. We'll do a solution and find out what the axial forces are. We'll thereby adjust the tau sub b for every member. We're going to come back then and adjust the stiffness for every member and run another solution. That's going to result in a whole new set of PUs, a whole new set of tau b's, and a whole new set of stiffnesses. So it's an iterative process. Let's see how that works within the program. If I come in here, first off, under the global parameters, you'll note that under the codes tab, whenever you choose the 13th edition, we have this additional drop down here that says adjust stiffness direct analysis method. And you have multiple options. You can say no. You can say yes, where we set that tau sub b value equal to 1.0 and leave it at that, which is actually allowable according to the code in certain circumstances. Or you can say yes, do an iterative solution. And when we say yes, iterative, the program is going to run up to 20 iterations on our structure in order to find a finalized stiffness. Now, the downside to running this iterative process is that it can slow down our solution time, certainly, since we need to run up to 20 iterations of each solution for each load combination. However, according to the AISC requirements, we must do this. So I'm going to come in here and set adjust stiffness yes to be iterative. And what we're going to find now in this P-delta model is that when I solve this with P-delta on and with that stiffness adjustment in there, that we've now lost some of our axial and flexural stiffness in the column, which in turn is going to result in a larger joint deflection at N2. We can see here it's now jumped up to 1.588, and a larger moment in this column. Now, instead of 140 kip feet, we're now up to 146 kip feet. So there was definitely a contribution due to that stiffness reduction. Now, one thing I would like to point out, too, is that you can control whether or not your members receive this stiffness adjustment not only by going to your Global Parameters Codes tab and setting it right here, but also if we take a look in the Members Spreadsheet under the Hot Rolled tab, you'll note near the end of the tab here, we have this function drop down for members, and you can choose between lateral or gravity. A lateral member is a member that's considered to be participating in the lateral resistance of the structure, and so therefore we are going to apply that stiffness reduction to it. Whereas a gravity member is considered to be not participating in that, so that will not receive the stiffness adjustment. Now, why is this important? Well, let's stop and think about floor beams for just a second here. In the case of a floor beam that's just a pin-pin gravity-only beam, we certainly don't want to reduce the flexural stiffness of that beam when we do our solution. And the reason we don't want to do that is because that floor beam is probably going to be controlled by gravity loads. And in the case of gravity loads, we don't want to basically artificially give a 20% increase in deflection by giving that 20% decrease in stiffness. So I'd probably want to set any of those members that aren't part of the lateral system over to be gravity in here. Now note that if you're using RISA floor, that we automatically take care of this flag adjustment for you. Okay, so let's come back over here. We've now met our second order analysis requirements, and we've met our stiffness reduction requirements. What about the notional loads? That's the third requirement of the 13th edition. And what we see here is that in the AISC's Code of Standard Practice, they have an erection tolerance set for columns, and that is that the column may be out of plumb by a distance of h over 500. So 1 over 500 over its height can be the out of plumb erection tolerance. And the AISC has come in and said that we need to consider the scenario where in a building, all of the columns in that structure have been erected out of plumb by the maximum amount in the exact same direction. A highly unlikely scenario, to say the least, but of course, as part of the 13th edition, they say that we need to consider this in our designs. And we can account for that by what's called a notional load. And that notional load is a fictitious lateral load that we place on the top of a column that's been modeled as vertical, and that lateral load has a value equal to P over 500, which is that out of plumb tolerance. So in other words, that's 0.002 times the axial load that exists within that column. So if we come into our example model here, we need to add a notional load, and we can do that by taking a look at the axial load, 200 kips, and 1/500th of that would be equal to 400 pounds. So now I need to come in and I need to edit my load, and instead of 10 kips, I need to say 10.4 kips. So with this 10.4 kips, I've now accounted for the fact that this column may have been erected out of plumb, along with my P-Delta and my stiffness adjustment. And when I come back and solve it for a final solution, given the notional load and everything else, we end up with a final design moment of 152 kip feet. Now, if we do this, one of the benefits that we get is that we are allowed to consider K equals 1.0. So K, the column effective length factor, was effectively a fudge factor in previous codes that allowed us to bypass the consideration of second-order effects, stiffness reductions, and column erection tolerances. And so now in the current code, we can simplify things greatly by saying that K equals 1.0 for everything, and then we just have to account for these three effects instead. Now, how does this work out in practice? Well, when we took a look at traditional design, this would have been used in the ASD 9th edition. You see that for our particular example, the moment would have been 120 kip feet versus 152 kip feet using the new direct analysis method. However, in traditional design, we would have had to consider a K value of 2.1 because it's a cantilevered column, whereas now we can consider the K value to be 1.0. And as a result, even though we have this larger moment, we have lesser capacity over here, larger moment, larger capacity, lesser moment, lesser capacity, it tends to come close to canceling out. And that explains why, even though we have to consider these additional three things, the P-Delta, the stiffness adjustment, and the notional loads, that we haven't seen buildings that were built under the Green Book falling down left and right. So we can see here that the required shape comes out to be actually slightly larger per the new direct analysis method. Now, this is just for one example here of this cantilevered column. In practice, you'll find that the columns that you come up with through direct analysis versus a traditional design method are going to come out to be about a wash. So they're going to be very similar. So it's basically a much more complex way of arriving at this fudge factor here that we've been using all along. So that's the gist of the direct analysis method. Next, let's talk for just a moment about warping torsion within members. And that is torsion that exists in open members such as wide flanges and channels. Traditional torsion design for closed members such as a tube or a pipe would have a constant shear flow throughout the section of that tube or pipe. But in a wide flange, we get an additional effect, and that's most easily represented by taking a look at the visualization of that wide flange as two WT members in minor axis bending. If you picture for a moment the idea that we take our wide flange and we cut it right here, and that we take the top as a WT with a representative point load going into the minor axis of it, and the bottom pointing in that direction, the value of these forces multiplied by the moment arm between them would be equal to the torsion that exists in this member. And this is a good approximation of what's happening in a much more complex way by using the Design Guide 9 warping torsion calculations for members. Now, if I come into the program, how do we account for that? What I'm going to do is I'm going to open up a new model here. And in this model, I have a frame of steel members. They're all wide flanges. And you can see that I've placed these point loads on here in order to induce a torque on the overall structure. And because all the members are modeled as fixed ends, we're going to get a torque on each one of these members. So when I solve this model, we can take a look at the deflected shape here. And let's look at that as rendered so we can see more clearly what's going on here. All right, here's quite a bit of twist occurring in all of these members. And you can see that distortion that occurs in the wide flange elements. Now, if I take a look at the design results for this particular model, what we're going to find in here is I get a shear value. Let's take a look at our maximum shear UC. I'm going to sort this spreadsheet from absolute max to absolute min, and we'll see here's my shear UC. This is my actual shear forces in the wide flange divided by the allowable of 0.656. Now, this is without considering warping torsion. I can confirm that by coming to the member torsion spreadsheet, and you'll see that we have an ordinary torsion shear. This is your standard St. Fernand's torsion. And then we also have the warping, but that's all listed as NC for no calc, because we haven't told the program to calculate warping shears as well. I can turn that on by coming into the global parameters. And under the solution tab, you'll see there's a checkbox for torsional warping. If I check that box, note that before we were at that 0.656 for our unity check. Now when I come back and solve the same model, here we see we're up to 0.670. So not a massive effect, but definitely a noticeable one. And we can see right in here that we're getting some warping shear in all these wide flange members coming out to be on the order of 1 to 4 KSI, which can be somewhat relevant, definitely. So warping torsion is an important consideration, and that's why the shear deformation and torsional warping boxes by default are checked within the program. But now at least you have a better understanding of what those boxes refer to, as well as, of course, this adjust stiffness method and the P-Delta that's required. Let's come back and take a look at another issue, and that is single angles. Single angles are something that the program used to handle differently from all other members, and in fact we still do. Originally in RISA 3D, because of the complexity of principal versus geometric behavior, we would only design single angles for axial loads, and we didn't consider them for bending. But recently we actually added the consideration of bending on single angles in so that you can get a code check for those as well. Now taking a look at this, what we can see is that a single angle has geometric axes, that is the local y-axis and the local z-axis. But if I do not restrain this angle, if I don't restrain both of its legs to act within these geometric axes, it's going to flip into a more natural set of axes for its behavior. This more natural set is called principal axes, or principal bending in this case. And what you can see is we have these principal axes called z prime and y prime. And this is the natural behavior of a single angle that has not been restrained against twisting. Now we can see the behavior of that in the program here. I'm going to pull open a model, and this model is showing us a simple roof grillage that's been set up using single angles. So it's a very basic model of all pin members, and we can see we have these single angle members modeled in here, and these are all 6 by 4 by 3/8 single angles. Now, if I come into the member spreadsheet under the hot rolled tab, you'll see that right now I have my unbraced lengths all left at blank, and this is the default. Whenever I draw a member, the unbraced length always comes in as blank. When I set an unbraced length to blank, one thing that we always know is that it's going to default to use the member's entire length as its unbraced length. So we'll have 10 feet for these members and 6 feet for those. But another thing to know on single angles is that if I leave my L-comp top and L-comp bottom both as blank, that means that I'm telling the program I have not restrained the top flange or the bottom flange. Now the top flange and bottom flange are really the top leg and the other leg on the angle. And if I have not restrained those at all, then the angle is going to be free to act about its principal axes. So now when I solve this model, I can come in and pull up a detail report for one of these single angles, and what we're going to see is that our moments that we get reported here get reported as MZ prime and MY prime, and that's opposed to an MZ and an MY. That's because we're seeing the moments about the principal axes of this single angle. So even though I've only applied a load in the vertical direction here, you note that on this angle, I actually have some bending about both principal axes. And that's to be expected since the principal axes are shifted, as I pointed out, from the geometric axes. A y direction load on here, when we start bending in principle, is going to have a y prime component and a z prime component. Now coming down a little farther here, we get our design based on bending about principal axes, and the same would also go for axial force in this member. We're going to get a combined bending and axial principal check here, and we can see that this beam actually fails. We have a bending check of 1.122, so it's about 12% overstressed for that single angle, and I can find that right here in my design results. Now, in practice, if I have this roof grillage set up, maybe I have some sort of plating or grating that's going to be on these angles that's going to restrain them from twisting. It's going to attach to them, and it's going to force them to act about their geometric axes. Well, I can represent that in the program by going to the members spreadsheet under the hot rolled tab, and I can set the unbraced length to be 0 for both the L-comp top and the L-comp bottom. And on a single angle specifically, if I tell it that the unbraced length is 0 for both L-comp top and L-comp bottom, I'm telling it that it's fully restrained against twisting, and then we'll get a geometric design. So when I come back into this same one now, you'll note that it's no longer MZ prime and MY prime, it's just MZ and MY, and we only have a moment in one direction about the geometric axis, so that gets reported. And here we actually pass as opposed to fail, because this angle is going to be stronger in its geometric axes than it was in its principal axes. So here we see 0.837, 0.377. A great trick to get single angles to work. Although bear in mind that if you are going to use this method, you need to make sure that in reality you are restraining these single angles against twisting. Otherwise, you're just building a model that has no correlation in reality, which we do see from time to time. Next, we're going to talk about some floor vibration within the program. And for that, I'm going to open up RISA floor. Now, we have the capability of calculating floor vibrations per AISC Design Guide number 11, and Design Guide 11 is all relating to the floor vibrations due to human activity, such as walking. So here I have this sample model with a really sort of wild layout here. So I have this beam that cantilevers out and picks up these beams. It's a strange floor system, to say the least. And let's say that this is going to be an office building, and I've designed this and created this. The load path is all correct, and certainly when I solve it, none of the members fail, not for strength or for deflection. But the question I'm going to have is this floor system going to have excessive bounciness? Floor vibration is commonly overlooked in terms of its serviceability criteria for building design, but it can be very important. Excessive floor bounce is a huge nuisance to the occupants, and it can actually cause some worry or concern among people, even though the structure is perfectly safe. Well, in order to understand that, we need to take a look at the criteria from Design Guide 11, which tells us that what we need to do is we need to find out the natural frequency of all of the floor beams within this structure, and then we need to apply a force to that frequency, or apply a force relating to that frequency that's going to represent a human footfall. And from there, we can actually find out how much acceleration is going to exist in the floor beams as a result of this. And we measure the amount of bounce in a floor system based off the maximum instantaneous acceleration up or down of the floor beam due to a footfall. Now, the first thing we do is determine the damping weight. And the damping weight within our program is going to be comprised of a few things. The first thing we're going to have is going to be the beam self-weight. That's automatically accounted for. The slab weight, well, where do we define the slab weight in RISA floor? Well, that's done under the deck definition spreadsheet under the loads tab. And here I have a composite deck for this building, so I'm saying that I have 50 PSF of this. And so the 50 PSF of slab self-weight plus the beam weight is going to act to some degree to dampen out the amount of bounce that's in the floor system, since it's a constant gravity load. And the last thing we have is what's known as a vibration load, or a realistic superimposed load. That is, how much actual live load and other superimposed load that's going to be in your structure can you reasonably rely on being in the entire structure? Now, certainly the ASCE 7 tells us to design for things like 50 PSF or 100 PSF for an office building, but that actual load, we wouldn't expect that to exist. And in the case of the design here for vibration, that load is actually going to overestimate our amount of damping if we used 100 PSF in here. So instead, we need to use a more realistic value. And Design Guide 11 tells us that for most office buildings, 11 PSF is a fairly reasonable estimate to account for things like desks and cubicles and file cabinets, so on and so forth. So you'll note that under the area load definitions, we have this VL vibration load that's in here. And this is basically a load that you can define to determine how much additional damping we're going to get in the floor system. So you'll note here for office, I have 10 PSF of superimposed dead in this model, 50 PSF of live, and I'm saying that I have 11 PSF of vibration damping load. And so that's very typical for an office. So as a result of that, what we're able to do is we're able to find what the natural frequency of is in the floor system. Now, the next thing that we need to do is determine that natural frequency, and the program can automatically take care of that for us, regardless of what our arrangement is in terms of framing layouts and the such. And then lastly, we need to compare the actual acceleration of the beams against an allowable acceleration. So let's take a look at the actual acceleration of the beams. What I can do in here is I can come up to my plot options, and you'll note that under the beams tab here, under show beams, I can change the color basis here to be the vibration acceleration. And I can actually hit OK on this, and this is going to color code my model according to vibration acceleration, although I have to have a solution first. Let me go ahead and run that solution, and then we'll be able to see how this looks. Now, another thing to point out is there's actually a shortcut button available through the custom toolbar where we can see this at a glance without having to go into the plot options. And I'll show you in a moment where we can add that button. But for here, we're just finishing up the solution now. It's determining not only the design of the structure, but also, as an aside, it's figuring out all the natural frequencies and the such. So here now you can see our beams are color-coded. I've got some yellow, some green, some blue. What do these correspond to? When I take a look in the upper right corner here, we're reporting the vibration acceleration, and this is basically reported relative to G, or the acceleration of gravity. So purple members here are going to have an instantaneous acceleration of roughly 1g, whereas blue members are going to have an instantaneous acceleration of less than 1/4 g. So certainly the purple members are going to exhibit quite a bit more of bounce to them than the blue members are, and we can see exactly how that frames out here. Now, according to Design Guide 11, based on a 65-pound excitation force, and that's considered to be a typical footfall, and that's what we have hard-coded into the program here, we have an allowable acceleration of about 0.5 g for things like offices, residences, and churches. Whereas for other more public spaces like shopping malls, where things are a little more active, you're not sitting at your desk paying closer attention to what's going on, you can actually increase the amount of allowable acceleration up to 1.5 g for situations like that. Now looking in our structure, 0.5 g would be represented by members that were either green or blue. And instead we have quite a few yellow members shown in the model here. These yellow members are clearly experiencing far too much vibration for what they should. Well, how do we rectify that situation? Well, one thing we can do is we can come to the member design rules, and under the member design rules, you can find that you can set a minimum and maximum depth for your members. In this case, I just have one design rule assigned to the entire structure. And so what I'm going to do is I'm going to set up a new design rule, and I'm going to call this new design rule beams. And I'm going to tell the program that all beams need to have a minimum depth of 17 inches. Now, why did I say 17 inches as opposed to 18 inches? Because in practice, what I'm going to do is force all these beams to be W18s or larger. Well, the reason I did that is because the program is going to take this depth very literally. And what you'll find is that some W18 members have a depth of 17.9 inches, whereas others have a depth of things like 18.1 inches. So in order to get around that nuance, since the program's just going to use this as a hard-coded value, we're going to say 17, which is halfway between a W16 and a W18. That ensures that no W16s will get picked up, but all the W18s will be considered. Now in our display, what I can do here is I can come in and say modify beams, and I can modify the design rules for all these beams here to be this new beams design rule that I've created, and I'll just say apply entries to all selected. Now when I solve, we're coming back in here, and considering these beams are all W18s, they're now going to have a much larger moment of inertia. That larger moment of inertia is going to result in them all having a modified natural frequency that's going to result in less bounce of the floor system overall. So just by upsizing these, we can see that now nearly all of our members are in the blue and in the green, with only a couple members coming up into the yellow. And the yellow may still be unacceptable, but for the most part, if the floor system is good, we know maybe this bay might be a problem area, and these bays here. But for the rest of it, we're going to have a fairly solid and stable floor platform to work with. So, important thing to know about that design. The last topic that we're going to cover today is steel joists. And so I'm going to show you how we handle these within RISA floor. So, if I come back into my RISA floor model here, let's take a look at my roof for a moment. You'll see what I have set up here are these steel joists, and they've all been sized to 16K2s. And we have some of these in here that are sized, and it puts SP after it. So I have 16K2 SP, 18K5 SP. When I come in and I visualize my load for a moment, what we're going to see is that I have a uniform line load placed along these joists over here. Let's shut off the display of those labels for a moment. Of 120 pounds per foot that's coming on there. And that could be a realistic load, but in this case, I'm set all these beams up as K-joists. And when we take a look at K-joist members, according to the SJI tables, all the tables have been set up for a uniform load. Well, how do we handle things if we don't have a uniform load? I mean, certainly it's realistic that we could have things like this snow load over here. Here's a tapering drift load going from 20 PSF up to 40 PSF on this side of the structure. How would we handle such a thing? Well, behind the scenes, what the program does is it smooths out your actual load into what's called an equivalent uniform load. In order to do that, we first take a look at the overall moment and shear that results from all of the loads that you've placed on this joist. From there, based off that overall moment and shear, we would back out what would an equivalent uniform load be that would result in that same maximum moment and maximum shear at the center and at the ends respectively. That would be called the W prime, or the equivalent uniform load. And so when I solve my model in the program, I can come in and find out on these joists. When I scroll down a little farther here, here's my actual live load on the joist, ranging anywhere from 225 pounds a foot down to 75 pounds a foot, but that we are actually designing the joist, if I come down a little bit farther, for a uniform live load of 175 pounds per foot. So this right here smooths out to be 175 pound per foot load, is most conservative and most correct according to those joist tables. Now, in order that we know that this joist has been designed in this special way, we need to notify that. We need to notify you in the drawings, and we need to notify you in the program here. So you'll see we have this 16K2 SP and an 18K5 SP. The SP means special. This is a joist that can handle the same amount of shear and moment as an 18K5, but it needs to be designed for the special consideration that we have a big point load existing at one point on that joist. And that point load is going to need to be specially reinforced by the joist manufacturer so that we don't get a localized failure of the chords of the joist or the such. And so we notify you right in here and give you these printouts such that you can actually use this information on your drawings in your specification to the joist manufacturer to tell them that, hey, I need these 16K2 SP joists, but they actually need to be able to handle a loading diagram that looks like this. And if you hand that off, that should be good enough to get a design for you. So that concludes the miscellaneous steel topics that we had to cover today, but we have additional resources. The AISC publications can certainly help you out. The RISA 3D help file and the general reference manual can give you a lot of information, as can our website, risanews.com. And of course, if you have any other steel questions that fall outside of the realm of what we covered today, don't hesitate to give me or anyone else here at RISA a call, and we'd be glad to explain it to you.